Hey everyone, welcome to Graphing Basics Assignment 8, where we'll be talking about symmetry and domain using interval notation. So let's start off with some questions. Call it bell work, if you will. The first one I have for you is, what can't I have under a square root? What numbers can't I have under there? Does the square root of 4 work? Sure. How about the square root of 3? Yeah, it's not a perfect square, but I could pull out my calculator and get a decimal approximation for it. Square root of 3 is 1.732 approximately. But what about the square root of 0? No problem, that's just 0. And then we come to the square root of -1. And that's an imaginary number. So, that's not a real number. It's imaginary. We can't have a negative under a square root. Now, if we had a cube root with a negative under it, that's no problem. But a fourth root with a negative under it, that's going to be imaginary again. So what can't we have under even index radicals? We can't have a negative. No negatives under a square root. Okay, that's going to be important today. Next. What can't I have in a denominator? Well, let's go through the same sort of process. I can have a 2, sure. I can have a 1, but I could even have a -1. So negative isn't a problem in the denominator, but what about a 0? Well, when we were talking about slope, we said that 0 in the denominator was undefined. So that's what we're going to say here, too. We're going to say, what can't we have in a denominator? We can't have no 0 in the denominator. Okay. All right. So we'll come back and talk about domain and how those restrictions, no radicals under a square root sign, or no zeros in denominators, in a few minutes. But I want to take a quick look at symmetry. There's lots of types of symmetry, as you learned in geometry class. We're just going to be looking at 3 types of symmetry. We're going to be looking at y-axis symmetry, x-axis symmetry, and origin symmetry. Our absolute value of x graph, remember our reference graphs with points at 0, 0, 1, 1, and -1, 1. This function has y-axis symmetry. We could fold it across the y-axis and it would lie on top of itself. This has y-axis symmetry. Okay? What about x-axis symmetry? Well, instead of, if this is y equals absolute x, what about x equals absolute y? X equals absolute y looks like this. Does this have y-axis symmetry? No. This point reflects down to this point. So we've got one negative one, and we have one positive one. This is an example of x-axis symmetry, where we're folding across the x-axis. And finally, origin symmetry is where we take a point and we reflect it through the origin. Now, that's certainly true with something like y equals x, but origin symmetry shows up in lots of situations. For example, our cube root of x graph. This point, negative 8, negative 2, goes through the origin and becomes this point, 8, 2. So this is an example of origin symmetry, where we're reflecting points through the origin. Okay? Now I'd like you to try and identify, based on just looking at the graphs, whether a given graph shows x-axis, y-axis, or origin symmetry, or neither. I mean, we can have things that don't have either x or y axis symmetry. So, for example, this parabola. This parabola has an axis of symmetry that runs down the middle, but that line of symmetry is not the x-axis, not the y-axis, and I'm definitely not going through the origin. So x-axis symmetry, y-axis symmetry, origin symmetry, or none of the above. Those are our choices in these next few problems. So let's take a look at some of our graphs. Y equals x squared. What do you think? X-axis symmetry, y-axis symmetry, origin symmetry, or none of the above? That's right, this is an example of y-axis symmetry. We see that this can fold onto that. How about y equals x to the third? Another reference graph. Well, if I think about this graph, I have this up-pointing parabola shape, and I have this down-pointing parabola shape. I could have the point 1, 1 here, and the point 1, negative 1 here. So, does this have y-axis symmetry? Does this fold across the y-axis? No. Does it have x-axis symmetry? No, I don't see this part reflected down here. What about origin symmetry? Does this point reflect through the origin to make that point? It sure does. There's origin symmetry. How about this one? X equals y squared. X equals y squared looks like positive square root of x and negative square root of x. Right? We could take the square root of both sides, don't forget the plus or minus, and get this. So we've got 1, 1, we've got 1, negative 1, and we've got 0, 0. So, x-axis symmetry, y-axis symmetry, or origin symmetry? How about neither? This piece folds down onto that one, so we've got origin symmetry here. Okay? So I have a visual way of determining what type of symmetry, but now I'm wondering is there a way I can tell just by looking at the ordered pairs I see on the graph? So, for example, what's happening here that makes this flip down and be this? Well, it's that the y values are the same number with opposite signs. So we would say xy becomes x negative y when we have, not origin symmetry. Why didn't you say something? This is x-axis symmetry. Yikes. So this is what we're going to see is true for x-axis symmetry. What did we see happening on the parabola, y equals x squared. So when we had y equals x squared, we had the point -1, 1, we had the point 1, 1, and we had the point 0, 0. In order for this to fold over onto that, what has to be true? Well, with x-axis symmetries, the y's had opposite sides. With y-axis symmetry, we've got xy becomes -x, +y. It's the x's that change sign for y-axis symmetry. And for x-axis symmetry, look, it's the y's that change sign. So is there something we could say about origin symmetry? What would be true about origin symmetry? When you look at those ordered pairs, -1, -1, 1, 1, 0, 0. Is it the x's that are changing sign? Well, yeah, they did. And what about the y's? Ooh. So origin symmetry, we see xy becoming -x, -y. Or we change the sign on both x's and y's. Okay? All right. Now, we got one other thing to talk about when we talk about symmetry, and that's the idea of functions and whether we have an even function or an odd function or neither. It turns out that, remember from last year in AB Algebra 1, functions pass the vertical line test. So when I look at some of the cases we've just noticed, our parabola y equals x squared, this thing we know has y-axis symmetry, but we also know that this is going to pass the vertical line test. So we know that y equals x squared is a function. And because it's a function, we've got some special function vocabulary. A function with y-axis symmetry is an even function. Now, don't mistake even function with an even power. It's true that this is an even number, but just because I see a squared doesn't mean I have an even function. For example, y equals x minus 2 squared. I see that even number up there as the power, but my graph for that function, and it is a function because it does pass the vertical line test, there's my graph of this. Now, does this reflect across the y-axis? Well, I don't see this shape over here. There is an axis of symmetry that runs down the middle through the vertex, but that's not at x equals at x equals 0. That's at x equals 2. So, even functions have y-axis symmetry, but just because you see an even power doesn't mean it's an even function. Even functions are things that have y-axis symmetry. Next, odd function. An odd function has origin symmetry. So when I look at our friend y equals x to the third, I see origin symmetry, and therefore I know that f of x equals x to the third is an odd function. But likewise, just like we saw with even functions, just because this is an odd number doesn't mean that every time you see an odd number there, you're going to have an odd function. For example, if we have x to the third x minus 1 to the third, we know from our transformations that takes the x to the third graph and shoves it right 1. What will that look like? Well, there's 1, and there's our graph. So this point, and at this point, does it reflect through the origin to make a point over here? No. So not every odd power is going to be an odd function. What determines odd functionness is if you see origin symmetry. If you see an ordered pair xy and its friend negative x, negative y, that's the sign of origin symmetry. So that's the sign of an odd function. Now, we had y-axis symmetry was an even function. We had origin symmetry was an odd function. What about x-axis symmetry? What type of function is that? Well, let's take a quick look. X equals y squared. We said this had x-axis symmetry because we saw the y value change sign. Same x, different y's. So this is x-axis symmetry. But what I notice is, does this pass the vertical line test? Why, no, it doesn't. So this is not a function. If what we're looking at has x-axis symmetry, it is not a function. It could be a relation. There's a relationship between inputs and outputs, but this is not a function because it fails the vertical line test. The only functions that we're concerned about are even functions, which have y-axis symmetry, and odd functions, which have origin symmetry. Those are the only special categories of function that we're going to be seeing, even ones and odd ones. Anything that's not even or odd, it's neither even or odd, so you don't really have to stress about it. Okay, so let's now do some classifying. I want to know what type of symmetry, if any, and I want to know, do we have an even or odd function, or neither, okay? So here's our first one. The line y equals x. Is that even or odd? You might want to pause the video, take a second to think about this. Come back if you're not sure or you're ready to answer. Well, I know this to be something that has origin symmetry because I see we've changed both x and y's as we reflected through the origin. Origin symmetry. And it's definitely a function because it passes the vertical line test. Might it be even or odd? Well, we know things with origin symmetry are odd functions. Okay, how about this one? y equals absolute x. Think about this. Does it have any symmetry? Is it an even or odd function? Might want to pause the video for a second while you think about it and come back when you're ready to discuss. Okay, so I notice that this point, 1, 1, becomes this point, negative 1, positive 1. When we change the sign on x's, but the y's stay the same, that's a sign of y-axis symmetry. Some people think y-axis symmetry means we change the sign on the y's, but that's not true at all. The y's have the same sign. It's the x's that are changing sign. And things with y-axis symmetry, do we know whether they're even or odd functions? Yes, we know that y-axis symmetry means an even function. Now, just because something has y-axis symmetry, is it always an even function? Well, let's take a look at this case. Oops. Earth. I'm drawing a circle. 1, 1, 0, 0, negative 1, negative 1, 0. Okay. This does have y-axis symmetry. It does have origin symmetry. It even has x-axis symmetry, right? Because I could fold this top down onto this bottom. The circle equation, x squared plus y squared equals radius squared, we'll talk more about that later, has all these types of symmetry, and even though it has y-axis symmetry, because this fails the vertical line test, it is not even nor odd. Since we have origin symmetry, I expected it to be an odd function. Nope, it's not an odd function because it's not a function. Remember, even and odd functions can only exist if this object is itself a function. Is this a function? Yes, it passes the vertical line test, so we know we have an even function because this thing that passes the vertical line test has y-axis symmetry. Okay, how about this one? Y equals x to the fourth minus 4x squared. What does that look like? That looks like this. There's negative 2, 0, there's 0, 0, and there's 2, 0. So, is this a function? Yes, it passes the vertical line test. Does this function have x-axis symmetry? No, because if it did, I'd see these things reflecting up here, and this part reflecting across as well. I don't see that, so it's not x-axis symmetry. Oh wait, of course it's not x-axis symmetry. Things with x-axis symmetry will never be functions. Does it have y-axis symmetry? Is this point reflected over the y-axis to make this point? Why, yes it is. So here I have a function that has y-axis symmetry, and therefore we can call this an even function. Okay. How about this one? Y equals cube root of x, one of our reference graphs. Passes through negative 1, 0, 0, 1, 1. Now, I think, yes, this is a function, but I think this function has origin symmetry. Can you explain why? That's a great quiz question, isn't it? Explain why this has origin symmetry. And the answer would be, of course, you see the ordered pair xy becoming the ordered pair negative x, negative y. We're changing the signs on both x and y. When we change the sign on both x and y, we know that we have origin symmetry. And because this is a function with origin symmetry, we know this is an odd function. Okay, the last thing I want to do with you regarding symmetry is to have you take part of a graph and complete it with different symmetries. So, for example, here's part of a graph. It's only the positive x's part of the graph. I need the negative x's part of the graph. Will you complete this graph if complete the graph for y-axis symmetry. Take a moment, draw this, and draw what it would look like if we had y-axis symmetry. Welcome back. If we had y-axis symmetry, we'd have something that looks like this. Our parabola has y-axis symmetry. But what if I had wanted instead x-axis symmetry? Can you complete this graph so that it has x-axis symmetry? Well, remember with x-axis symmetry, we'd be taking these points and changing what? X-axis symmetry, therefore we change the y's. xy becomes x negative y. So I'm going to have this point here with the same x, but the opposite y. And I'm going to have this point here with the same x, but with the opposite y. In fact, I think because this is in red, I'm going to draw this in red. There we've completed the graph so that it has x-axis symmetry. Is this something that has is a function? No, it fails the vertical line test. Anytime we have x-axis symmetry, we will not have a function. Okay. And what if I needed to complete this graph for origin symmetry? So let's take out our x-axis symmetry. How would you complete the graph for origin symmetry? Well, we know that these points have to reflect through the origin, and both x and y change signs when we do that. Oops. To -4. And so there's my completing the graph for origin symmetry. Okay? Now I think it's your turn. Okay. Here's part of a function. Well, part of a relation. And I'd like you to complete this graph A with origin symmetry. Give it a try. Come back if you're stuck or when you're ready. Welcome back. So with origin symmetry, we know that everything has to reflect through the origin. We know that we change the signs on both x and y. So I'm going to have this point over here, called -1, -1. And when this shoots through to here, we're going to change the sign on both. Well, -0 is the same as 0, but I'll have -2, 0. And so my graph will look like this. And stop, because this stopped. Okay, that's with origin symmetry. Now, can you complete this graph B so that it has x-axis symmetry? take a moment to complete this graph with x-axis symmetry. And with x-axis symmetry, we know that we're supposed to change the sign on just the y values. So this point up here, 1, 1, is going to become this point down here, 1, negative 1. 0, 0 stays the same, 2, 0 stays the same, and I'm taking this shape and flipping it down here. This is definitely not a function, but it does have x-axis symmetry. And then the last one I would like you to do is, of course, y-axis symmetry. Please complete this graph for y-axis symmetry. Okay, when you did you remember to change the sign on the x's? So we're going to have this point here, negative 1, positive 1, and this point here, negative 2, 0. And then it looks like that. This is y-axis symmetry. Okay? I hope you're feeling pretty confident and comfortable with x-axis, y-axis, and origin symmetry. I hope you're feeling okay with even and odd functions. Even and odd functions is not going to be important for us much this year, but those of you moving on to calculus, it'll be important. The last thing I want to talk about today is what we started class with. I want to talk about domain. Now, we know that domain is the set of all possible inputs. What does that mean? What numbers can you plug in? So if I have the square root function, I can plug in 1, I can plug in 2, I can plug in 3/4, I can plug in even 0, but I can't plug in negative numbers. And so we say the domain here is restricted to positive numbers. And last year, you might have written something like that with inequality notation. Yeah, I'll be marking that wrong this year. Not because it is wrong, but because every time we talk about domain, I need interval notation. You must learn interval notation. If you give me this, I will mark it wrong. Please give me interval notation. Now, what interval are we talking about? Well, if we're talking about the domain for square root of x, it's all these numbers, including 0. Because 0 is included, I put a bracket on 0, and then I go forever in this direction. So, my domain is, for square root of x, bracket 0 to infinity. Okay? So those are all the numbers that I can plug in. What if I have something like y equals square root of x minus 1? We know from our transformations that this is the square root graph shifted to the right one. And so therefore, on a number line, if that's 0, can I plug a 0 in there? No, because 0 minus 1 is negative 1, and I can't take the square root of negative 1. Can I plug in a 1 there? Yes, 1 minus 1 is 0, and the square root of 0 is 0, so this works. I mean, even if we just think about the graph shifted over 1, we can see that the domain starts here and goes over. And so I would have bracket 1 to infinity again. What if I changed that minus 1 to a plus 1? Okay, so in this situation, I know from my transformations that I've shifted the graph left 1, and now my graph looks like this. So what would the domain be here? What are all the possible x values that I could plug in here? Well, I can plug in 0 and get this y value, and I can plug in 1 and get this y value. I can even plug in negative 1. Negative 1 plus 1 is 0, and the square root of 0 is 0. But I can't plug in anything to the left of that. Negative 1 is included in my domain, and then we go forever. And by forever means I can plug in any of these x values. and we'll get a corresponding y value. But sometimes it's going to be really hard for me to figure out, like in this case, x squared minus 2x minus 8, what the domain is based on thinking about transformations. I really can't think about this with transformations, not in any easy way. So instead, let's go back to this one for a second and say, we said we couldn't have negatives under the radical. So I say x has to be greater than or equal to 0. And therefore, x can be 0 or all the way up to infinity. So there's inequality notation, which we don't want to see this year unless specifically asked for, and this is interval notation, and we do want to see that. That's the assumed notation we'll use for domain. Okay, now, what if we have something like y equals square root of x minus 1? Well, I'm going to use that same idea of taking x minus 1 and setting it greater than or equal to 0. I'll add 1 to both sides, and I'll see x is greater than or equal to positive 1. So, on my number line, 1 is included, and so are all the numbers bigger than that. So, I'm going to have a domain that looks like this. I can take what's under the radical and set it greater than or equal to 0 to help me figure out what the domain should be. So let's practice doing that. If I have y equals square root of x plus 4, I'm going to take what's under that radical and set it greater than or equal to 0. So I know x is greater than or equal to negative 4. On a number line, that looks like this, so my interval notation will go from negative 4 to infinity. Okay, but Mr. Kukla, I could still do that one with my transformations. So let's try something a little harder. How about something like 4 minus x? Because a lot of students say that the domain for this one is going to be 4 to infinity. And then I have to mark it wrong, and they're all sad. Why? Because they didn't take what was under the radical and set it greater than or equal to 0. So I'll add x to both sides, and what do I notice? I notice that 4 is greater than or equal to x, or if I read it backwards, x is less than or equal to 4. On a number line, could be equal to 4, could be less than 4. Look at that. That's not from 4 to infinity. No, no, no. If I plug a 5 in here, I get 4 minus 5 is negative 1. I can't take the square root of negative 1. No, my domain here starts at negative infinity and goes until I get to 4 with a bracket. That's my domain, okay? So, now that we have a sense of what domain is, will you tell me about the domain for square root of 2x plus 3? Pause the video, take a few moments to figure out the domain, and don't forget to write it in interval notation. Okay, welcome back. So I'm going to take what's under the radical and set it greater than or equal to 0. I do that every time I have a square root. I'll subtract 3, and I'll divide by 2. If I think about this on a number line, here's negative 3 halves. This tells me negative 3 halves is included, and I want the x values that are also bigger than this. Do they live over here? No, they live over here. This is our domain graphically, and if we use interval notation, negative 3 halves to infinity. Okay, how about this one? Y equals square root of 6 minus x. Okay, take a moment to find that domain, write it in integral notation, and come back when you're done. Welcome back. Just like with the others, I'm going to set what's under the radical greater than or equal to 0. Now, I know many of you want to subtract 6 and divide by -1. That's 2 steps, and I'm just going to do one step and say that 6 is greater than or equal to x, or if I read it in this direction, x is less than or equal to 6. So on a number line, here's 6, could be equal to, these are the numbers less than, and so I've got negative infinity to 6 with a bracket. Okay. Starting to get the hang of it? Excellent. God.